You wake up tomorrow, and gravity is just 1% weaker. Doesn't sound like much, does it? A 1% discount, a 1% battery increase, trivial. But this isn't the price of your coffee. This is the operating system of reality. The moment you swing your legs out of bed, you feel it. Your brain, a finely tuned prediction machine calibrated over millions of years of evolution and decades of your own life to exactly 9.8 meters per second squared, makes its first error of the day. You expect a certain resistance, a familiar pressure as you plant your feet, but it's soft. Spongy. You overshoot, stumbling forward like a newborn foal, your inner ear screaming that something is deeply, fundamentally wrong. You make it to the kitchen. You go to pour a cup of coffee. The liquid arcs from the pot in a lazy, wide stream, splashing out of the mug because its ballistic trajectory is no longer what you've learned to anticipate. The mug itself, as you lift it, feels eerily light in your hand, like a cheap prop. Your own arm feels disconnected, overpowered. You've spent your entire life lifting things in a consistent gravitational field, building an intuitive physics model in your very bones. That model is now obsolete. A bird outside your window flaps its wings with the same power as yesterday, but now it soars upwards too sharply, its flight path unstable and clumsy. Then you turn on the news, and your personal disorientation becomes global panic. Bridges, engineered to bear specific loads under a specific gravitational stress, are now understressed in ways their designers never intended. The subtle flex and tension that holds them together is off balance. Structural harmonics are shifting. Some of the world's most iconic suspension bridges begin to sway, gently at first, then more violently. In orbit, the International Space Station, which maintains its altitude through a delicate dance of velocity and Earth's gravitational pull, begins to drift. Its orbit is now slightly too high, its speed slightly too slow for the new, weaker gravity. It's on a slow, inexorable path away from Earth. The same is true for all our satellites. The global positioning system, which relies on atomic clocks ticking in a precise gravitational field, is now a chaotic mess. Your phone's map can't even find your own house anymore. And the Earth itself, our planet, is a sphere because gravity has relentlessly pulled it into that shape over billions of years, balancing against its own internal pressure. With gravity weakened, that balance shifts. The planet would begin to expand minutely, but enough to trigger a wave of global earthquakes and volcanic activity as the tectonic plates adjust. The moon's orbit widens. Tides become less predictable. And that's just a 1% change in one constant. Now imagine the electric charge of the electron was off by 1 part in a million. The rules of chemistry, the force that binds atoms together to form molecules, would be rewritten. Hemoglobin might not bind to oxygen. The double helix of DNA could unravel. The complex chain of proteins in your body that regulate everything from your heartbeat to your thoughts would fold into the wrong shapes, becoming useless lumps of matter. The very atoms that make you would start to come undone. Your body isn't just a body anymore. It's a slow-motion chemical catastrophe. Our reality, our very existence, is balanced on an impossibly sharp knife's edge. Every single second of every single day, we unconsciously bet our lives on the fact that the universe will keep its promises. That gravity will pull, that light will travel at its designated speed, and that atoms will hold together exactly as they did a nanosecond ago. But this raises the most profound question in all of science. Why? Why are there rules at all? Why isn't the universe just a featureless, lawless chaos? Are these laws of physics timeless, ironclad commandments, written in platinum ink on a scroll that existed before the Big Bang even happened? Are they Platonic ideals, perfect and unchanging, which the universe must obey? Or is it something stranger? Something more unsettling, and maybe more beautiful? Could it be that the laws we see aren't eternal dictates, but rather emergent patterns? Are they cosmic habits that the universe fell into, that hardened into reliable promises over billions of years, simply because they were stable? Today, we're not just asking what the laws are. We are putting the laws themselves on trial. We are auditing the rulebook of reality. To understand where laws might come from, we have to start with the deepest foundation we've ever found, the intimate connection between symmetry and law. Now, when you hear the word symmetry, your mind probably jumps to a butterfly's wings, or the mirrored perfection of a Rorschach test. In physics, the concept is far more potent. A physical symmetry is a vow. It's a guarantee from the universe that if you change your point of view in a certain way, the laws of physics, the fundamental rules of the game, will not change one bit. Let's make this concrete. Imagine you're a scientist in a completely sealed, windowless laboratory. You perform a classic experiment, dropping a steel ball and measuring its acceleration due to gravity. You get 9.8 meters per second squared. Now, without your knowledge, a secret team transports your entire lab from New York to Tokyo overnight. You wake up, you repeat the experiment. Do you get a different number? No. You can't tell you've moved. This is spatial translation symmetry. The universe doesn't have a favorite location where the laws work differently. What if you perform the experiment on Tuesday, and then again on Friday? Will the ball fall differently? No. This is time translation symmetry. The fundamental laws of physics don't care what day it is. They are constant in time. Finally, what if you rotate your entire laboratory by 45 degrees? When you drop the ball, does it suddenly veer sideways because down is now in a different direction relative to the lab? Of course not. It falls straight down towards the center of the Earth, just like before. This is rotational symmetry. The laws of physics don't have a preferred direction in space. For decades, these symmetries were noted as interesting, elegant features of our mathematical descriptions of the world. They were beautiful, but their true significance was hidden. Then, in 1915, while the world's great male physicists were focused on Einstein's new theory of gravity, a brilliant German mathematician named Emmy Noether uncovered a truth so staggering it connected these abstract symmetries directly to the concrete stuff of reality. Her discovery, now known as Noether's theorem, is one of the most beautiful and powerful ideas in all of science. It's a cosmic Rosetta Stone. It proves, with the absolute rigor of mathematics, that for every continuous symmetry in the laws of physics, there is a corresponding conservation law. A quantity in the universe that is strictly, absolutely conserved. It cannot be created or destroyed. It's a cosmic budget that can never, ever be unbalanced. Let's look at our symmetries again through Noether's eyes. That symmetry in space, the fact that the laws are the same whether you're in New York or Tokyo, what is its conserved quantity? It's momentum. The reason an object in motion tends to stay in motion, the reason a fired bullet carries its forward impetus, the reason you feel a recoil when you throw a heavy object, all of this is a direct consequence of the universe not having a favorite place. If you could move to a place where momentum wasn't conserved, you could essentially create a perpetual motion machine, getting free push from the universe. But space symmetry forbids it. What about that symmetry in time, the fact that the laws don't change from Tuesday to Friday? This is even more fundamental. The conserved quantity it guarantees is energy. The first law of thermodynamics, the conservation of energy, is not just a good idea, it's a mathematical consequence of the laws of physics not changing over time. The energy in the food you eat is converted into the chemical energy in your muscles, which is converted into the kinetic energy of your movement, and the heat you radiate. It transforms, but the total amount is always accounted for. It's the ultimate balance checkbook of the cosmos. And rotational symmetry? That gives us the conservation of angular momentum. It's why a spinning ice skater pulls her arms in to speed up. It's why a gyroscope remains stable. It's why planets maintain their orbits and their spin. The universe's vow not to have a favorite direction means that rotational motion has a sacred, conserved quantity. Symmetry is not just about aesthetics. It is the architectural blueprint for stability. It's the universe giving you a receipt and saying, look, things might get incredibly chaotic. Stars might explode, galaxies might collide, but this number right here on this receipt, the total energy, the total momentum, that will stay the same, no matter what. These aren't arbitrary rules someone made up. They are unavoidable consequences of the universe's fundamental indifference to where you are, when you are, or which way you are facing. Okay, that's incredibly profound. Our most basic laws of conservation are direct results of symmetry. But this just pushes the question one level deeper, doesn't it? Why are the symmetries so perfect? And more importantly, does this tidy picture of symmetry explain the messy, complicated rules we see all around us? Because when we leave the pristine world of fundamental equations and look at the real world, things get complicated. Unbelievably messy. How does this clean, elegant symmetry produce the gritty, complex reality we actually live in? This leads us to one of the most subtle and powerful toolkits in modern physics, the idea of effective field theory, and its engine, a mathematical beast called the Renormalization Group. Together, these ideas represent the universe's profound art of not sweating the small stuff. Let's go back to that hurricane. You would never, ever describe a Category 5 hurricane by trying to create a list of the position and velocity of every single H2O molecule involved. The data would be meaningless. It would be a blizzard of information that told you nothing about what the storm was actually doing. Instead, you use a completely different, effective language to describe the hurricane at its own scale. You talk about things like wind speed, atmospheric pressure, the diameter of the eye, and the storm's path. These are emergent properties. Wind speed isn't a property of a single water molecule. It's a collective, statistical property of trillions of them. It's the right language for that scale. The universe operates in the same way. Down at the tiniest, highest energy scales imaginable, far smaller than a proton, physics is a frantic, boiling chaos. Quantum fields are constantly fluctuating, virtual particles are popping in and out of existence, and everything is interacting with everything else in every conceivable way. It is the water molecule level of reality, and it is a nightmare of complexity. But you and I, we don't live down there. We live up here, at the hurricane level. We are the emergent, large-scale phenomena, and the laws we experience are the effective laws for our scale. The Renormalization Group is the mathematical machinery that allows us to zoom out. Imagine you're at an art museum, standing with your nose pressed against a giant painting by Georges Seurat. All you see is a meaningless, chaotic jumble of individual dots of pure color. Red, blue, yellow. There's no image, no form, no sense. It's the microscopic chaos. Now take one step back. Some dots begin to merge in your vision, blurring together. Take 10 steps back. Now you can see shapes forming. Patches of color that look like grass, or a hat, or a dress. The individual dots no longer matter. Their collective effect is what you see. Take 100 steps back, to the other side of the gallery. The dots are completely gone. You see a beautiful, coherent image, people lounging in a park on a Sunday afternoon. You see a story? The chaotic micro-details of the dots have flowed into a simple, elegant macro picture. The freckles on a face vanish, but the smile remains. Our laws of physics are that smile. They are the stable, large-scale patterns that emerge after all the chaotic, high-energy details, the frantic dots of the quantum world, have been averaged out, blurred together. Renormalization shows that as we zoom out in scale, or go down in energy, the behavior of a system flows towards stable endpoints, which physicists call attractors. These are like deep, wide valleys in a vast landscape of possibilities. Countless different rivers of microscopic chaos, countless different arrangements of the dots, all end up flowing into the very same valley, and thus they produce the exact same large-scale behavior. This leads to a truly miraculous concept called universality. It's the shocking fact that many completely different microscopic systems can behave identically at macroscopic scales. It's why the physics of water turning to steam at its critical point can be described by the exact same mathematics as a magnet losing its magnetism at its critical temperature. The underlying details are completely different, but they belong to the same universality class. They flow to the same valley. The details of the dots don't matter for the final painting. This insight is shattering. It means the simple, elegant laws we cherish, Newton's law of gravity, the laws of thermodynamics, the rules of fluid dynamics, might not be fundamental truths at all. They are almost certainly effective laws. The emergent, low-energy, zoomed-out rules of a system whose true, high-energy nature is almost unthinkably complex. The laws aren't the bedrock of reality. They are the calm surface of an infinitely deep and turbulent ocean. And there is one more pillar in this classical toolkit, perhaps the most elegant of all, the principle of least action. Imagine you're on the beach and you see someone drowning in the water. You're a lifeguard. You need to get to them as fast as possible. What is the quickest path? Is it a straight line? No. Because you can run on sand much faster than you can swim in water. The optimal path, the path of least time, is to run a longer distance along the beach and then enter the water at an angle to swim a shorter distance. Your brain intuitively calculates this path of least action, in this case, time. It turns out, the universe does this for everything. Of all the infinite possible paths a thrown ball could take to get from your hand to the ground, it follows one specific parabolic arc. Why? The principle of least action states that the universe is efficient, almost artistically lazy. It will always choose the one path through its configuration space that minimizes, or sometimes maximizes, a specific quantity called action, which is roughly the effort expended over the entire journey. It's a cosmic budget of motion and energy. In the 20th century, the great physicist Richard Feynman elevated this idea to a sublime new level with his path integral formulation of quantum mechanics. He showed that at the quantum level, a particle doesn't take a single path. It takes every possible path simultaneously. It travels in a straight line, it zigs and zags, it goes to the moon and back, all at once. Each path has a certain action associated with it. But when you add up the contributions of all these infinite paths, something magical happens. For the vast majority of crazy, meandering paths, their quantum phases don't line up, and they destructively interfere with each other. They cancel out into nothingness. The only paths that survive this cancellation are the ones clustered around the path of least action, where the phases line up and reinforce each other. The classical world we see is the one trajectory that survived the quantum vote. This turns our physical laws into an incredible form of data compression. Instead of a messy description of infinite possibilities, The law of gravity is a tiny, elegant piece of code that summarizes the one path that emerges from the quantum chaos. A short poem that captures a vast library of might-have-beens. So with these powerful tools, symmetries that give us conservation laws, renormalization that extracts elegant simplicity from mind-boggling chaos, and the principle of least action that selects the most efficient story, we construct our standard models of particle physics and cosmology. And these models work with a precision that is frankly absurd. Our prediction for the magnetic moment of the electron matches experimental measurement to 1 part in a trillion. That's like measuring the distance from Los Angeles to New York and getting it right to within the width of a single human hair. We predicted the existence and properties of the Higgs boson decades before we built the LHC to find it. We predicted the ripples in space-time from colliding black holes a century before LIGO detected them. Our laws, our models, are the most stunningly successful intellectual achievements in human history. But they only work where they work. And at the absolute boundaries of our knowledge, deep inside the singularity of a black hole, at the first instant of the Big Bang, or when we stare into the dark abyss of dark matter and dark energy, our beautiful models shatter. The floor gives way completely. The map is not just incomplete, it's blank. And this is where we must abandon our comfortable certainties and venture into the truly radical territory. This is where we have to seriously ask if the rulebook itself is an emergent property of the universe. Welcome to the frontier. Welcome to the dizzying land of law without law. This electrifying phrase was coined by one of the 20th century's most imaginative physicists, John Archibald Wheeler. He posed the question so revolutionary it threatened to upend all of physics. What if there are no preordained, timeless, transcendent laws at all? What if the universe started as a lawless chaos, and the regularities we now observe as laws didn't precede it, but emerged from within it? Wheeler's guiding mantra was it from bit. This is the radical, profound proposal that at the absolute bottom of reality, we will not find matter or energy, or even space and time. We will find information. The answer to a yes or no question. A binary switch. A single bit. To get your head around this, think about the screen you're watching this on right now. It displays a rich, complex, moving image of a person talking. It's an it. But what is it fundamentally made of? If you zoom in far enough, it's just a grid of pixels. And each pixel's color and brightness is determined by a string of ones and zeros. At the bottom, the complexity of the video is made from the simple bit of the code. Wheeler proposed that the entire universe works this way. Every particle, every force, every inch of spacetime is in it that is built from an underlying code of quantum bits. But if everything is just information, where do the laws come from? Wheeler's idea was that they emerged through a kind of cosmic consensus. Imagine the early universe as a vast, participatory democracy. Every quantum interaction, every measurement, every time two particles affect each other, it's like a vote being cast. In the beginning, there were no rules, just random interactions. But over time, certain patterns of interaction might have proven to be more stable than others. These stable patterns would have reinforced themselves. A quantum conversation takes place, and as a consensus is reached, a regularity emerges. Think about how language evolves. There's no grand council that dictates the rules of grammar from on high. Grammar crystallizes out of the collective act of billions of people trying to communicate with each other over centuries. The rules of language are an emergent consequence of the interactions themselves. The laws of physics, in Wheeler's view, could be the same. They are the grammar that the universe has agreed upon over 13.8 billion years of continuous conversation. The rulebook is the average of countless interactions, not an edict from a cosmic king. This line of thinking gets even wilder and more concrete when we look at the fabric of reality itself, space-time. A growing number of physicists at the cutting edge suspect that space-time is not fundamental. It's not the pre-existing stage on which the drama of reality unfolds. It is a projection. A hologram. And it's built out of something far stranger, quantum entanglement. Entanglement. Einstein called it spooky action at a distance. The bizarre, instantaneous connection where two quantum particles share a single existence, a single fate, no matter how vast the distance separating them. Measure the property of one particle here on Earth, and you instantly know the state of its entangled partner in the Andromeda Galaxy. What if this spooky connection is the fundamental thread from which reality is woven? Picture a vast, disorganized jumble of these quantum threads of entanglement. It has no structure, no dimensions, no sense of here or there. It's a pre-geometric chaos. But now, imagine these threads start connecting in highly organized, complex patterns. Certain bits of information become more entangled with some bits than with others. A network structure forms. According to the ER=EPR conjecture, this network of entanglement is spacetime. The geometric sense of distance, the fact that this point is close to that one, but far from another, is a direct reflection of the density of entanglement threads connecting them in the underlying quantum information. What we perceive as smooth, continuous 3D space is a macroscopic illusion, generated by the architecture of this incredibly complex quantum web. In this framework, gravity is no longer a fundamental force. It's not about curved spacetime. It's an emergent, statistical phenomenon. It is, essentially, the thermodynamics of entanglement. The laws of gravity are to the underlying quantum information what the laws of temperature and pressure are to the motion of individual atoms. It's a collective, average effect. But this raises a critical question. This quantum information is incredibly fragile. A single stray interaction can break an entanglement, a phenomenon called decoherence. So if our spacetime is built from these delicate threads, why is it so robust? Why doesn't the universe just decohere into a chaotic mess? The answer might be one of the most stunning convergences of ideas in science, coming from computer theory, quantum error correction. Think about how your computer sends information over the internet. It breaks the data into packets, and in those packets, it includes redundant checksums or parity bits. If a packet gets corrupted by noise, the receiving computer can use that redundant information to detect the error and reconstruct the original message. It's an error-correcting code. It seems the universe discovered this trick first. The way quantum information is entangled to form spacetime appears to be arranged in a massively redundant, highly efficient quantum error-correcting code. The information about any one region of space is not stored just in that region, it's smeared out non-locally across the entire entanglement network. It's like a hologram. If you cut a holographic plate in half, you don't get half the image, you get the whole image, just at a lower resolution. Spacetime is like that hologram. Even if huge chunks of the quantum information are lost or corrupted, decoherence happens locally, the overall global structure of spacetime, the message itself, remains intact. The laws of physics as we know them, in this picture, are the checksums. They are the stable, self-correcting protocols of this unimaginably vast quantum computer. Reality, it seems, has its own autocorrect. But if laws can emerge from an underlying code, it opens another, even more startling possibility. Could the laws themselves evolve? Physicist Lee Smolin proposed a breathtaking theory he called cosmological natural selection. It is Darwinism applied to the whole cosmos. The theory goes like this. Every time a star in our universe collapses to form a black hole, the singularity at its heart could trigger a bounce, a new Big Bang that creates a daughter universe on the other side. But here's the crucial twist. When this new universe is born, the fundamental constants of physics are slightly, randomly mutated. The strength of gravity might be a tiny bit different. The mass of the electron might be nudged up or down. The speed of light could change. Suddenly, you have a mechanism for cosmic evolution. You have reproduction, new universes from black holes, and you have mutation, randomly tweaked parameters. All you need is selection. What makes a universe fit to survive and reproduce? Well, to make black holes, you first need to make lots of large stars. To make stars, you need the laws of physics to be just right for gravity to clump gas together, for nuclear fusion to ignite, and for galaxies to form. So, universes whose randomly mutated laws are better at producing stars and black holes will have more children. They will leave behind more descendants in the multiverse. Universes with sterile laws, those where the constants are so out of whack that stars never form, will have no offspring and their particular set of laws will die out. Over countless generations of universes, this process would naturally select for laws that are highly optimized for producing black holes. It's an explanation for the shocking fine-tuning of our universe. We don't live in a universe that was magically designed for us. We live in a universe that happens to be a descendant of a long line of fertile ancestors, a universe fine-tuned for cosmic fertility. Against all these beautiful, speculative visions stand a series of deep, stubborn paradoxes, unsolved mysteries that keep physicists staring at their blackboards at 3 a.m. First, the one we just touched upon, the fine-tuning problem, also known as the Goldilocks enigma. The fundamental constants of our universe appear to have been set with the preternatural precision of a master locksmith. They are just right. For instance, the energy density of empty space, the cosmological constant, is fine-tuned to about 1 part in 10 to the power of 120. If it were even slightly larger and positive, the universe would have expanded so fast that galaxies never would have formed. If it were slightly larger and negative, the universe would have collapsed back on itself moments after the Big Bang. Or consider the process of fusion in stars. For stars to create carbon, the fundamental building block of life, an atomic nucleus must achieve a very specific resonance state. Fred Hoyle, the astrophysicist who discovered this, said that his atheism was deeply shaken by it, claiming the evidence suggested a superintellect has monkeyed with physics. Why is our universe walking this impossibly thin tightrope that allows for complexity, stars, and life? Is it a lucky accident, a sign of Smolin's cosmic evolution, or something else entirely? Then there's the hierarchy problem, a puzzle of scale that is simply baffling. It asks, why is gravity so ludicrously, absurdly weak compared to the other fundamental forces? The electromagnetic force that holds a tiny magnet to your fridge is powerful enough to overcome the gravitational pull of the entire Earth. Numerically, gravity is about 100 million trillion times weaker than the weak nuclear force. It's like comparing the sound of a single pin dropping to the sound of a Saturn V rocket launch. There is no accepted explanation for this colossal gap, this hierarchy, between the forces. It is one of the biggest embarrassments in theoretical physics. And finally, there's a subtler puzzle, the simplicity problem. Out of the infinite landscape of possible mathematical structures and rules, why are the laws of physics that govern our universe so simple? So elegant? Why can the entire standard model of particle physics be written on a coffee mug? Why can we compress the behavior of the cosmos into a handful of beautiful equations? The space of all possible laws should be an untamed jungle of nightmarish complexity. Is our local patch of reality just an unusually well-manicured garden? Did some process, like renormalization, smooth out the complexity? Or are we just not smart enough yet to see the true, horrifying complexity that lies beneath? So let's perform one final stress test, a thought experiment. Let's rewind the cosmic clock all the way back to the first picosecond after the Big Bang. A hot, dense, roaring chaos of energy and quantum fields. Now let's run the simulation again, but stir the primordial soup just a little bit differently. Let the initial quantum coin flips all fall differently. Would the same rulebook emerge? If our laws are just stable attractors, deep valleys in the landscape of possibility, is the landscape designed such that the universe would inevitably flow into the same valleys, rediscovering the same symmetries and effective laws every single time? Or is the landscape full of countless different valleys, and our universe just happened to fall into this one? Could a different roll of the quantum dice have led to a universe with 7 fundamental forces, 20 types of quarks, and laws of chemistry that would be utterly alien to us? Are our laws inevitable, like the crystalline structure of a snowflake, or are they contingent, like the specific path a river takes to the sea? We simply don't know the answer. And that is both terrifying and exhilarating. This changes our entire relationship with reality. If laws are emergent attractors rather than eternal decrees, then the incredible stability we rely on for our very existence is not a rigid, static fact. It's a dynamic equilibrium. It's not a stone foundation, it's a perfectly balanced spinning top, actively maintained by countless unseen flows and feedbacks. And on our small, human scale, what is technology if not the art of harvesting these invariances? We are pattern exploiters. Your GPS works because we have learned to trust the ridiculously stable patterns of general relativity. The semiconductor transistor in your phone is a monument to our faith in the conservation of charge and the rules of quantum mechanics. We build our entire civilization in the deepest, most stable valleys that nature has carved for itself. Our predictive power is not an act of reading a divine rulebook, it's an act of aligning ourselves with the universe's most ingrained habits. This forces upon us a new and profound epistemic humility. Our models are maps, not the territory. A beautiful equation like E equals mc squared is a sublime poem of compression, capturing a universe of meaning in just a few symbols. We should trust the compression. We should celebrate the poetry. But we must always be prepared to question the ink. We must remember that the map could be a low-resolution rendering of a much more complex, and perhaps stranger, underlying reality. We began this journey by worrying about our coffee falling. And we end here, at the precipice of a worldview-shattering possibility, that the universe is not obeying laws at all. It is in the process of becoming them. We may be living in a cosmos that is still learning, still settling, still writing its own autobiography. Reality is not a finished book we are trying to read. It is a living language, and we are catching it mid-sentence. And our role, as strange, temporary, local, conscious auditors of this cosmos, is to listen with all our might, to learn the grammar of emergence, to document what we find with rigor and honesty, and to have the courage to keep asking, who or what is writing the next line? The audit isn't over. It will never be over. If you want to dive even deeper and question another fundamental pillar of reality, the nature of time itself, then click the video on your screen right now. It's the next step on this journey. And now, a question for you. If you could be a cosmic legislator for just 24 hours and tweak one law or constant of physics, what would it be, and what's the first thing you would do? Let me know in the comments below. I want to read the most creative, chaotic, and beautiful ideas you have. Finally, if you believe that questioning the very foundations of reality is what makes science the greatest adventure of humanity, then subscribe and join the Science Audit. We question everything, because that is the only way we learn anything. Thank you for watching.